Yeah. Last time we finished up learning about the linked idea, right? The link structure, where we have nodes that connect to other nodes. The nodes are relatively simple data structures. They just have usually, depending on the type of node you're dealing with, but your typical run-of-the-mill node is going to have two fields. A data field, which is going to be whatever you want to store. That's kind of like what you want to put. If we're making an analogy to an array, the data is, well, what type of array do we want? Like what are we storing in there? So that's what the data is in the node. And of course the nodes also have the next field as well. And that's to get to the successor. That's to get to what comes after that node, right? In an array, if I have something in index 7 and I say, well, what comes after that? You all go like, well, okay, it's index 8. Why? Because that's how arrays work. In a node, if you are at some arbitrary node and I ask you, well, what comes after it? You just got to go through the next field instead. So that's the difference there. But both the array and the link structure are interesting containers. They're different ways we can store information. We can easily store stuff in an array. You know, an array is this like linear container. It starts at index 0, goes to index whatever. Where the link structure, it's like a linear container too, right? We could start with the head node, the node at the beginning of the structure that has some data, and then what comes after that? Well, next, 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 and so on, right? You just go. So, it's kind of neat. They're similar, but they're different. We can use them to do the same, to achieve some of the same stuff though. So we saw an array stack, so let's make a linked stack. There we go. So I know we briefly started this at the beginning of last lecture, but I'm going to go back to the beginning of this one. So a linked stack. So we already implemented a stack as an array stack. But we now see that we can use a link structure. So we already wrote our stack Java interface. So here, if I go here and I go look at stack, we have our interface. Don't need that, don't need that, don't need that. Yeah, we have our interface. And remember, the interface is just defining what a stack is in terms of what it does. But it doesn't say anything about how it does anything, remember. So a stack, if I want to have a stack, the stack must push, pop, peek. We can check if it's empty and get its size. We can add more stuff, of course, but at the very least, if we want to write a stack, it has to have these things. And if I go back to array stack, we'll see, okay, we've got our constructors, but we've got our push, our pop, our peek, size is empty, and I have a toString here as well. Now I can go here and if I go here, because at the top here, I say public class array stack implements stack. Because I, as the programmer, am saying, this is implementing a stack. Meaning I want this thing I'm writing to be a stack. The implementation is an array stack, but I want it to be a stack. Because I say that, Java is now forcing me to implement everything a stack can do. If I don't, then it's not a stack. Then it is, by definition, not a stack. If I go here and I get rid of any of these methods here, that is in the interface, so peek was there, and I just ditched peek, well, peek's not there, and now it's saying, nah, class array stack must either be declared abstract or implement abstract methods peek. It's saying, it's not a stack unless you got peek. I can do the same thing with size and empty, right? If I go up here, it might only warn me about one. Yeah, so it's saying like, oh, okay, well, you're missing methods that are required in order to make this thing an actual stack. Oop. There. So now we can come along and say, okay, well, I don't want an array stack. I'm going to make a, let's make a linked stack. Linked stack class. And it's going to implements stack. There. Oop. There. I've started a linked stack. I want to implement a stack. I want to write a stack. I want to write the how for a stack, but that's implemented with a link structure, not an array. So let's do this. Well, what do we need, right? We need, okay, first of all, we know we need to have our these. We need to have our push, pop, peek, is empty, and size. They're just methods that at this point, they're not doing anything. They exist. So now this is a stack. It's just there's no actual implementation here. Like pop, return null. Well, that's not helpful, but it's here to, I'm starting it. So we need these methods. We're going to need constructors, right? And we also need a way to keep track of the size. So, okay, let's create a field. Private int size. Okay. And we also want to keep track, like with the array stack here, we had an array of type T that had stacks, right? And this stacks, called stack. It was a reference variable to an array of type T, called stack. And top served two purposes, right? Top kept track of both the size and also where the next available spot on the stack was in the array. Where here, what we could do is always have the head of our link structure be the top of the stack. Because if you remember, if we go back to previous, and we think of the link structure, if we have this here, if the head is always the top, we saw that adding to the front was a relatively simple procedure. Adding to the middle was a pain, but adding to the front wasn't too bad. You have your new node, you make your new node reference the old head, and then you have head reference the new node. So we do that, and then that, and now we have a new head. So this would be like pushing on the stack. Just add something to the front of the link structure. And then adding to the middle, we don't need to worry about that right now for this. And then deleting from the front. This is probably the easiest operation. Just say head. I know you used to point to this, whatever color that is, teal, green. Well, now, I want you to reference your next, actually, which is the yellow one. So pushing is adding to the front of a link structure, and popping is just removing from the front of a link structure. So instead of needing to hold on to a whole array, a reference to a whole array, all I need is to have a private int, a private node, because we need our node. And we wrote our node class in I think for the previous topic, node of type T called head. There. We can call it top, I guess, too, but we'll call it head. So that's what we need here. This is everything we need. We need our constructors. Okay, let's throw that in public link stack there. And I guess when we make a new stack, well, the size is 0, right? And the head, well, the head will be null. We don't need. When the stack is empty, there's nothing there. So yeah, okay, the head is null. That's easy. So now I think we're basically set. We just now need to implement push, pop, peek, is empty, size, and maybe a toString. Because we've got our push, pop, peek, is empty, size. All right. Now, let's go back to the actual content and make sure I'm not missing anything big here. Next. So stack. Okay, all we have to do is implement these things. Remember, it says nothing about how. Okay, linked stack. So here's the idea of what we're going to have. Our stack, I guess I called it top in this figure here. Have that reference some node at the beginning, and we're going to keep track of the size. Whenever I want to push something, well, it's just adding to the front. We put something in front of top, and then make it top. Pop, you remove the thing from the top. Pop again, remove the thing again. So here's how we got it here. So I guess here I called it top. You know what? I guess I'll go back and change it to top. Top. There. And now top. just to have a little bit consistency there. So we've got size, top, and then we set them. The constructor is just going to have nothing there. Cool. And yeah, we got our constructor. Great. So like the array stack, we want our link stack to implement everything in the interface. Well, that means we need to implement push, pop, peek is empty in size. I know, a broken record. So before we carry on here, though, let's make a couple more observations about the difference between the array stack. See, with the array stack, we had this final constant here, default capacity. And we had two constructors. One where you just make an array stack that just creates an array stack with whatever the default capacity is. So this is like our default constructor. And then we have another constructor that takes some specified capacity and set the top to 0 and create a new array of size capacity. But with our linked stack, we don't need this default capacity because the array had a fixed size. You know, we got around that with our expand capacity. We just say, okay, well, if we ever run out of room, just make a new array, double the size of it, copy everything over, and just pretend everything, you know, our array is just bigger. Where with the linked stack, we have no such limitation. We never need to expand capacity. There's no such thing as a capacity here. I mean, you could talk about capacity once you get to like, oh, you've run out of like literal space on your computer. That's not going to be an issue for us. So we don't need that capacity thing anymore, which is pretty cool. Also meaning that when we push, we don't need to expand capacity. Peek, okay, great, is empty. You know what, let's finish is empty in size. Okay, so size, return size. Okay, that's easy, is empty. We always like to do the if size is 0. All right, if size is equal to 0, this is true. Therefore, is empty returns true. If size is not equal to 0, this expression returns false, and then we return false. That's all. Cool. So we've started the link stack, but we haven't really implemented any of the important methods other than saying they exist. Questions now. I've been talking for a while. I need questions. Or is everyone A-okay with all this? I'm expecting questions. I want to hear at least 1 or 2 good questions before I keep going. Is everybody there? Okay, what would be a different use case for these? Interesting. So we don't know. So do you need an if statement with the return? Do you not need an if statement with the return? Okay, I'll get to yours in a second, Nels. But Muskrat, the different use cases, well, there are 2 different implementations. Remember, in computer science, there's an infinite number of ways to solve any of these problems. And we're just looking at 2 different ways to go about doing it. Is one better than the other? Well, it depends. A lot of times with good implementations in computer science, we'll say like, well, there's no free lunch. You know, there's pros and cons with this one, but there's pros and cons with this one. This one's good in scenario A, B, C, but this one's good in X, Y, Z. So they're different. And in the next topic, the algorithm analysis, we'll actually spend some time sinking our teeth into that comparison. So sit tight on that. Very good question. And Nels, is this what you mean? Do you mean like if size, oops. Oh. Else. Yeah, I think I got confused when you said if. I know what you did. Oh, okay, cool. Yeah. So yeah, we don't need this. And in fact, look, I think if statement can be simplified. Oh, IntelliJ, look at that. Being super smart for us. Yeah, we only need this because size is true. This expression gets evaluated to true or false. And whatever the evaluated version of this is what is empty returns. Size is 0, that's true, return true then. Size happens to not be 0, like it's 7, okay, size is 7 equals 0, well that's false, return false, that's all. This right here is a common beginner programming mistake. But again, look, you're overthinking it. You're overthinking it. You're overthinking it. What is this? This right here is an expression that returns true or false. So if this is true, return true. If this gets evaluated as false, return false. Well, you're working too hard. You're working too hard. Just look at this. And we go back to this. This is much nicer, cleaner, and simpler. I realize I say you're working too hard, but it's kind of funny to like mentally jump to that because this comes with experience. But, you know, hopefully you look at this and go like, yeah, that is a little cleaner, isn't it? Anyways, other questions. All right, so carrying on, we'll get to the push. I'm not even gonna look at this. Okay, we want our push. Okay, so what we'll do is we'll take the element. So element is something of type T. Now, first thing we gotta do is we gotta like create a node to put that element into. All right, so a node of type T I'll call it toPush, equals a new node, and it is going to take T. Oh, no, element. Great. Uh-oh, what am I doing wrong here? How did I write my node? Where's my node? Oh, I guess all right, this is how I wrote my node. Whatever. Basically what I was doing is I thought I wrote a node where I had a constructor that would take the data immediately. I guess I'll have to set the data after I create it. So I create a new node to push.setData to element. And then what's this write only object? I don't know what this is whining about now. And then here, all we have to do is remember, when we insert to the front, the new node, you reference what the top is. Okay, pardon me. No, the new node, your next, is what the top is. So we'll say, okay, toPush, set next. Nope, set next is what? Well, that's the top, right? Then top, you equal toPush. And then size, size plus plus, increase size. So what all has happened here? Create a new node. Let's draw this. Okay, so in this particular scenario, let's draw out a couple examples. Let's see, make this a little bigger. So we have top. It's a reference to null at this point in time. I come along and I make toPush, which is a reference to a node with some element E in there. I set its data and I set its next to what top references. Okay, great. So your next now points to null. Cool. And then top, you equal what toPush equal or is referencing. So we go like this. That method finishes, this reference variable disappears because it only exists inside the push method. And suddenly now top is this. This is great. Now, if we think about, let's see if I can do another push here. Okay, so now I come along again and I say, okay, let's add another one. I'm going to make it green this time just to show it's different. And all right, gray. Now a new node that has some data E in it. And I say, okay, your next is what top references. Okay, great. That one. And then top, you reference what toPush references. Oh, okay, so don't go there anymore. We go there. That triangle's pretty rough. But now top is this one, and its next is this one, and its next is, well, null. So this is pushing to the front. That's all we got. That's all we need to do. I expect some questions though, because you might be still going like, you know, something doesn't seem quite right here. So let me know if you have any questions. So you'll see in this particular example, I do have a node that takes, that has a constructor that takes the element. Cool. I didn't write that here. Oops. I didn't write that in mine, so I'm stuck with the default constructor, but you know what? Let's write one. Okay, node. And then element, your next is null, and then we can replace this one with just this with null. There. Great. So now I have another constructor where I can actually give it the data right off the bat, meaning I can go and just put that there, and then we don't need to set the data anymore because the constructor will now do that for us. I mean, we can add another constructor here if we really want, and I can do something like this. Element, node of type T, next. So if this happens, we'll just say next. This, nope. This dot next. Okay, cool. So there we go. And then I can just chain this one along and say, well, this is this with element and null. So now I've got some kind of freaky constructor chaining here, but we'll take a second and look at this. Here, it's a constructor where I can say, immediately upon creation, assign element to be like the data field, and then next is whatever's next. If I come along and I do not specify a next, but I do specify the element, well, I'm just going to immediately call this constructor, and the reason we know it's this constructor right here is because it's the one that takes two of the correct type here. Element null, element next. But null is going to work here. So if I only specify the data, I just call this constructor, which sets the element and then sets the next to null. And then if I ever call a regular old node with no parameters set, I just say, okay, well, immediately call this one, which assigns element to null, which then just immediately chains to this one, which assigns element to whatever element was, which was null, and next to null. If you don't like what I just did, don't worry about it. I was being fancy. But it does allow me to do something neat like this. Top. Nope. Top. There. Yeah. So now I can very easily... Local variable toPush is redundant. You're right. Look at that. Look at that. I did it all in one line there. Look at that. That's magical. Element. Why is it green now? Yeah. So look at that. Oh, my push is now so simple. But I'm going to go back to this one because I think it's perhaps a little clearer to... Like the code is perhaps a little cleaner or clearer or anything. So let's compare it to what we wrote here. Create the node toPush, element of type T. By the way, you don't need to specify this. Java's smart enough to know, like, okay, yeah, it's going to be of type T. Element, set the next to top. Top is push, size ++. Push, set the next, top is size ++. Cool. Questions about this push. And notice, there is no need for expand capacity. We could just keep pushing things on this stack forever. Any questions about any of that? All right, well, if you have one, throw it in the chat. You guys are being awfully quiet today, so here's hoping you're all doing okay. Or maybe you all understand this and you're in great shape, so that's good. But if you have questions, ask the questions. Okay. In push, notice how we're just adding to the front of the link structure. Yes. Is top treated as a node? Yes. Top is a reference to the node. Okay? So top is a reference to a node of type T. So when I say top is equal to toPush, well, it's like, okay, you now reference the node toPush, which is this one. And then when I say toPush set next to top, well, top is a reference to a node. Set next needs a reference to a node that that node could reference. So yeah, top is just a reference to a node. In the same sense that in node, next is just a reference to another node. Good question. All right, so close the array stack. Now we need push. Now let's look at the pop. Okay, pop. If toPush is top, how can its next be top? Because, remember, it's sequential, right? If you're thinking all of this code is happening at the same time, no, it's one line at a time. So if we draw it out, if I have, I'm going to draw it out again because I think it's important to emphasize this, because you're right. It might seem a little funny. It's like, well, hold on. You just said toPushes next is top, and then you made top itself. Does that just not change toPushes next to itself? Like, if that's what you're thinking, that's a reasonable thought. But remember, I have a node. I'm going to draw the node as a box this time. And the node has two variables in it, data and next. So when I come along, if this is top, T-O-P, okay, and then I create a new node, and its next is who cares, right? And then I have toPush is here. There, I hear a boop. Let me just check. I will in 1 second, Kim. All right, so I have toPush, and it's that. Okay, that's my arrow. Great. So when I say, hey, toPush, set your next, so this is N for next, N for next. What I'm saying is, remember that this really top, it's not a node, it's a reference to a node. Push is not a node, it's a reference to one. So it's a variable that contains the information we need to get to this node. So when I say toPush, set your next, I'm copying this over. All of this right here, I'm copying this, which means, oh, make a copy of that, which is a reference to this node. Right here, this one. Then when I say, okay, top, u equal to push, well, I copy this over to here, which then makes this point to there, right? So all that's changed. So it's because I took this value, stored it in this variable here, which was the field for that node. And then I took the value that here, stored there, and switched it out with whatever toPush was referencing. So I definitely get why you're thinking, wait, you just set it's next to something else. But remember, they're not the nodes, they're references to the nodes. And that's what's being stored here. So I can copy over the contents of this, put it here. And that's why, okay, it's copied, it's saved here. Then I change what's in here. But once it's copied, I'm pointing at my screen, you can't see that. Once it's copied here, I mean, this is safe from change. If you're thinking it's something kind of like, where like, oh, when I copy this over, it's a reference to this, which is a reference to this, and then you change it to, that's not what's happening. Remember, it's copying over the actual contents of what's in there. Did that answer your question, Muskrat? Okay, cool. And remember, in this week's lab, you'll be playing around with the link structures too, so it'll help. And Kim, can I go back to the node for a second? Yes. What about the, you got a question. What's up? It's got the two fields. Yep. Oh. Is null like none? Yes, null is none. Yes, it's a special value that just means nothing is here. And you might, and if you've ever seen like null pointer exception, well, that's the same as like none. Wow, none has no field. I can't remember what Python says, but it's the same thing. One thing I will note is, let me finish this class first. None type, it's its own special value. Okay, link stack. I'm gonna close the node for now. So pop peak. Peak is even easier. All we have to do is return the top get data. Because peak doesn't remove anything. All we do is just return top get data, right? Hey top, what's your data? But there's that catch, right? And this was the same issue with the array stack. What do we do if they try to peek on an empty stack? Well, realistically, the person trying to peek should know beforehand if it's empty or not. Meaning, if it ever happens that someone tries to peek on an empty stack, similarly with pop, something bad has happened. So what we'll do is we'll pass that message to them. So if is empty, we'll throw an exception. We will say something bad happened. Throw new no such element found exception. And we like to throw in a message here. Peek on is bad. There. Peek on empty stack is bad. Because it's no good. Okay? So if it ever happens to be empty and someone's trying to peek an empty stack, like what would make sense? Like if I return null, well that's no good, because if I'm returning null, does that mean the top's data was null, or does that mean it doesn't what does that mean? So here the idea is, if you peek, you're gonna get whatever's there. If nothing's there, we throw the exception because something bad has happened. And we could do the same thing here with pop. Pop, except here we'll pop on empty stack is bad. There. But finishing up peek, yeah, all we have to do is say, hey top, what's your data? And then return that data. There. That's it. That's the peek. Nothing needs to change beyond that. But pop is a little different because we want to get the data to return, but we also have to remove the thing at the front of the stack. So first things first, to return equals top dot get data. So I'm going to get the data from the top and save it to a variable called toReturn. Then I want to say this. If I go back to previous, I hear a boop, just 1 second. Then this is what I want to do. This is deleting from the front. Say, hey, head, you're actually your next. So head, give me your next. Oh, that's this yellow one. All right, head, you equal that now. Oh, okay, great. In this case, head isn't head, it's top, but same thing. Top equals top, get your next. So we'll say, okay, top, you are now equal to top dot get next. Yeah, that's it. We say, hey top, what's your next? If we go here, we say, okay, hey head. Okay, green one. Who's your next? Oh, well, that's a reference to this yellow box right here. Great. Head, you're equal to that. Oh, so I'm now a reference to this yellow box. Great. And then at the end, return to return. Oh, but I also size minus. I want to save this first because if I do top equals top.getNext, I can't get the data after top after I've just like lost reference to it. So I'm going to save it first, replace top with its next, decrease the size, and then return the thing. Bunch of boops. For clarifying, just clarifying, top is only a reference to the first node, not a node. So top.getData returns the data of the first node. Yes, absolutely yes. So, Cause yeah, head is not a node. So when I say head, give me your data, that's, oh, head, oh, this node, get your data. Head, get your next, oh, that's this reference here, you know, that's what that is. Very good observation. And fork, that right there is an important thing to note. This is a big area of confusion for people when they start with this. It usually cleans itself up quickly once you get a little bit of practice under your belt. But sometimes people kind of lose the idea that, like, wait, no. Like, top is not a node. It's a reference to a node. So, yeah. And then guest, why do you write is empty instead of something is empty? Good question. So, it's because I'm calling the method from within here. So I'm just calling the is empty method right here. If I want, I could say this, this dot is empty. Then I would be like, oh, I'm calling this object, this one's is empty, which is totally fine. This. So that's why. It's because I'm calling, well, which is empty? Well, the one defined inside this class. If I wanted to, like in my lecture here, if I wanted to make a stack of type integer equals a new linked stack, if I want to call the is empty, if I wanted to call is empty on that stack, well, I would say stack dot is empty, right? That is this, well, that's this method right here. But because this method peek is using it from within its own class, we don't need the this. That's why. Did that clear it up for you? Yeah, okay, cool. All right. Oh, or oops. Do we not have to delete the node that is now referencing the same as top? Fantastic question. So, if we go... So, what you're asking is, I have a node here. I have a node here. Here we have. So this was there, and then I just said, okay, no, top, you're now this, right? So your question is, well, hold on. What do we do about this guy? Is that what you're asking? Yes. All right. So to go back, what I'm saying is, okay, I just got the data out. Nope. And I have top referencing the top. But I'm popping. I want to remove this node. So I get the data out of it. Great. It's saved, ready to get returned. I then say top equals top, get your next, and then, you know, boom. There we go. That's what it is. Now, nothing references this. In Java and in Python, if it ever so happens that something exists in your computer, in RAM, that was created, but there is now no way to ever get back to it. So there is now, once I did this, nothing references this node anymore, meaning it is now impossible for me to get back to that. So don't do this unless you know you're good to get rid of this node. Because imagine I didn't take the data out yet. I still have the data. It's like, okay, top equals top, get next. All right, get the data out of the thing that was top. Well, how do I get to the old top? I can't. It's gone. Like I now have no way to get to it because top was how I got there, but I just said top is equal to its next, which is here, and I can't go this way. That's not an option. I can't go backwards. So I'm stuck. I'm in big trouble. So that's why we get the data out first. If we ever lose reference to it, what will happen in many modern languages is something called garbage collection comes along. So garbage collection will come along and be like, this thing right here is taking up space in the computer, but nothing is referencing it, meaning it's useless. So you know what? Doesn't exist anymore. It'll delete it for us. So we don't actually have to specifically delete. In some other programming languages though, they don't have built-in garbage collection. So if we ever do something like that and you leave that node there, let me go back, and you leave that there and you don't delete it, this creates something we call, does anyone know what we call this? If this exists and we don't delete it, because our language doesn't support garbage collection and we're responsible for all our data getting deleted. Anyone know what we call that? Lag. Nope. It's called...
It's a memory leak, right?
It is a memory leak. Who said that?
I did.
Yeah, okay, but who's you?
Anakin.
Anakin, well done. It is a memory leak. That's exactly correct. So what happens is, you might say, well, okay, this node takes up like a couple bytes in the computer, right? Like that's not a lot. But imagine this program was running for like a year and a half, doing a lot of calculations, and you're not deleting this stuff. Well, eventually that's gonna like add up over time, and then your program is wasting space on your computer, and that's bad. So yeah, that's called a memory leak when that happens, which is neat. Fortunately, in Java, we do not need to deal with that. Fortunately, Java does go and delete it for us. But the downside of this is there is some computational overhead associated with garbage collection, meaning a programming language with garbage collection will be inherently a little bit slower. There's 1,000 asterisks attached to the statement I'm making right now. But there is some computational cost to have this process done automatically for us. Within certain other programming languages where you have to do it yourself, there's no garbage collection running at the same time that needs to manage this. So, you know, you win some, you lose some. A boop. How long after does it do that? There is a there's a complex process that we're not going to worry about. But we're not going to worry about it. You can go learn if you want, but it's outside the scope of this course. Interesting question, and it is an interesting process, but we're not going to worry about that right now. So yeah, this is fantastic. We don't need to do that. And I think this all works. Right? So I think I've implemented my stack. Now I'm going to show you. Now, a lot of people, raise your hand in the chat if you were like, yeah, I still don't get this whole interface thing. This feels like an extra step. Like, okay, I've got an array stack that implements a stack and a link stack that implements a stack, but they're both stacks. Why do I even bother that? I'll just implement the push pop peek is empty and whatnot myself. And leave your hands up because I want to see. So a bunch of people still feel like, okay, what's the whole point? Well, so here's where the magic happens. So I'm going to go to my lecture 1. And if I go to lecture 1, and I'm going to go back to the array stack. So I'm going to take all this right here, this testing code at the end. It's not a real testing code, but I'm just copying all this. And there. No such element example. Import. There. Who remembers that the key, the hotkey for doing fixing the indentation? Because I can't remember. Oop. Well, if you can't remember, that's fine. Neither do I. I'm just going to fix this because I don't want it to be ugly. Control Alt L. Well, there's time and also how much RAM is currently being used of the total RAM allocated to Java. Okay, so here is my code for the array stack, right? So I have an array stack, capacity 5. I hit run. This should all work correctly. Perfect. Perfect, perfect, perfect. Everything's working as it should. We top, you know, I'm asking all these questions, and then we see the exceptions here, but that's because that's down here when I'm saying, hey, peak when it's empty. I should see a no such, you know, and that's why we see, oh, I guess I didn't for the array stack peak. I didn't actually write a message in here, but that's okay. So Here's where the magic is. Back to lecture 1. My stack must be a reference variable to a stack. It doesn't need to be an array stack. It just needs to be a stack. So I can do this. I'm gonna get rid of this because we don't need that initial capacity. I'll rerun it just to make sure everything's fine without that capacity. Okay, good. So I can come along and do this. Linked stack, hit run. It all works. Oh, I didn't write my 2 strings, so we don't see it printed out. But now I have switched out. I didn't need to change anything here. None of this code needed to change here. Because my stack is a stack. And if it's a stack, I know it's got push, pop, peek, is empty, and size. Because linked stack is a stack. So Java, it's like a contract. If the programmer writes, well, it implements a stack, it means that I can say, well, stack, my stack reference variable can reference a linked stack because it is a stack, or an array stack because it's a stack. Why are they stacks? Well, because I implemented the stack interface. So I can guarantee that the reference variable, my stack, is referencing something that I can push, pop, peek, size, and is empty. I can change out the whole backend implementation of the stack with changing half of a line of code, changing half of the name of the class, right? So linked stack, array stack, boom, it's gonna work just fine. Linked stack, it's gonna work just fine. If I didn't, if linked stack does not do this, despite implementing push, pop, peek, is empty, size, even though it's implementing all those things, because it's not implementing the stack interface explicitly like this, if I get rid of that, it's now gonna say, no, we got a problem here because I can't, like, you're saying it's a stack, but like, I'm gonna run here, run. Yeah. Now it's complaining about types. The problem is I'm saying this is a stack of type integer. It's a stack. But linked stack isn't referencing, or linked stack is not a stack implementation. So Java has no guarantee that this is safe. So it's gonna say, nope, no, not gonna do it. It'll work if I do this. Right, now it's happy, it'll work just fine because I'm specifically saying, okay, oh, what did I do wrong here? Oh, it's not overriding anything. Well, that's just a tag thing. This is fine, but I had to make the reference variable to a linked stack. I don't want to do that. I want to keep it nice and general. I want it to be a reference variable to a stack. So it's with these interfaces, implements stack type T, that we can create like a contract to say, like, I promise you as a programmer, I'm implementing a stack. Then whoever comes along and uses my implementation of a stack, because I said it's a stack, they know they can show up. Let's say you implement a whole new thing called like my super best awesome stack. My super best awesome stack. Obviously it doesn't exist, but if you wrote a my super best awesome stack class and it implemented a stack and you did it correctly, this is guaranteed to work. Bill Gates can call me up and say, hey, I got an even better implementation of a stack that's gonna make your program way better. All you have to do is just create it. It's called my super fantastic best awesome stack. Boom, there. Now my billion-line program is using a better version of a stack that's gonna make it so much faster. So there's one of the huge benefits of interfaces, is I can guarantee facts about my data structure, and I know I can use them safely. So it's awesome. Anyways, we are out of time, so I'll stop the recording